Hello, and welcome to your second logistic regression lecture. In the last lecture, we ended by talking about the loss function log loss. This is a metric that allows us to assess the performance of our model where lower values of that function are indicative of a better performing model. That's not the only way we can measure the performance of a classification model. And just to be clear, these metrics that we're about to talk about apply not just to logistic regression, but to every classification model that we're going to learn. Before we dive into the metrics, we need to know about the four different things that go into them. So let's talk about the confusion matrix. A confusion matrix is a table that gives you information about the guesses that your model made. In the case that you have a binary outcome, so either a 0 or a 1, there's basically four things that can happen. On the main diagonal of our confusion matrix, we have the two ways that our model can be correct. The first way we can be correct is if we guess that something's a positive and it actually is. We call this a true positive. Our guess was a positive, and that guess ended up being true. The other way we can be correct is if we guess that our item is negative, and it is indeed negative. In other words, a true negative. Our guess was negative, and that was true. If you combine the number of items on that main diagonal, you get the total number of times your model guessed correctly. On the off diagonal, you get all of the times that your model guessed incorrectly. The first way we could be incorrect is we could guess that our data point is negative, and it actually was positive. Thus, we call this a false negative because we guessed negative, but that was false. Lastly, we can get a false positive. A false positive occurs when you predict that something's going to be positive, but it ends up that it actually was negative. For instance, a false positive on a COVID test would mean the test says that you're positive for COVID, but you actually don't have it. Whereas a false negative would be when the test says you don't have COVID, but you actually do. Taken together, these off diagonals tell you how many times your model was incorrect. All right, now that we've talked about confusion matrices, let's see how we can use these four different values to create different metrics of how well our model performed. First up, we have by far the most common one, which is accuracy. Accuracy is just how many correct predictions a model got divided by the total number of predictions it made. The higher the accuracy, the better performing the model. Accuracy answers the question, how often is the model correct? However, there's other things we might want to know about our model. For instance, we have the sensitivity, which is also sometimes called recall. This answers the question, how often is the model correct for positive cases? So in this case, we're only looking at this top row of the confusion matrix. For cases that are actually positive, how many of them did we get correct? For instance, if you've taken a COVID test and you've read that leaflet that comes with it, you might have seen things like the sensitivity of the test. This basically says for people who have COVID, how accurate is your test? Next, we have the specificity. The specificity answers the question, how often is the model correct for negative cases? This only looks at the bottom row of our confusion matrix. And you can think of, for instance, a pregnancy test. We want to make sure that our pregnancy tests have high specificity because a pregnancy test could just tell everyone they're pregnant and the sensitivity would be great. Out of all the true positives, we would predict all of them correctly. But it would have really poor specificity. For people who aren't pregnant, it would predict that all of them are pregnant. Next, we have precision. This answers the question of all the cases where we predicted positive, how many of them were actually positive? This only looks at the left-hand column of our confusion matrix. We want to make sure that when our model says something is a positive, that most of the time it is actually a positive. And next we have an F1 score. An F1 score doesn't have as intuitive of an interpretation as the other metrics we just talked about because basically it's calculated as a combination between precision and recall. So if you want a metric that tells you both about precision and recall at the same time, you're going to want to use an F1 score. Last but not least, we have an ROC AUC value. The ROC AUC value is based on an ROC curve. An ROC curve is a plot that compares the sensitivity of a model to 1 minus the specificity of that model. In other words, it plots the true positive rate on the y-axis and the false positive rate on the x-axis. Now, when we have a model that outputs something like a predicted probability, traditionally what we do is we make the threshold 50%. Anything that has a probability above 50% we categorize as a 1, and anything below 50% we categorize as a 0. But we don't have to use that threshold. We could use any threshold that we want. And the ROC curve basically tells us about the trade-off of when we move the threshold, how that impacts the true positives and the false positives from our model. In the next slide, we're going to talk a little bit about how we create an ROC curve, but for right now, I want to give you some reference values. So a model that basically does nothing and is just randomly tossing a coin to decide what category to put something in would have an ROC curve that looks something like this. This is basically the baseline we're operating from. A perfect ROC curve from a model that perfectly discriminates between positives and negatives is going to have an ROC curve that basically looks like the axis of the plot. Most of the time, we're going to be somewhere in the middle. If your curve is below this baseline, so anywhere in this shaded area, that means that something has gone significantly wrong. One thing that's really nice about ROC curves is that we can use them to visually assess the performance of our model. For instance, here, when looking at the yellow versus the blue curve, we can tell that the blue curve is better at distinguishing between our two categories because its curve is closer to the upper left-hand corner of the graph. Now, so far, we've just been talking about the curve, the ROC part of ROC AUC. AUC refers to the area under the curve, and it's basically a way to quantify our curve with a single number. If we look at our baseline model here, the area under this curve is going to be 0.5 or 50% because 50% of this graph is underneath that curve. For our perfect model, our ROC AUC is going to be 100% because 100% of the area of this graph is underneath that curve. However, for most models, our value is going to be between 0.5 and 1, like for this curve where it might be something like 0.7. The higher your ROC value, aka the closer to 1, the better our model is at distinguishing between positive and negative cases. So in this graph, we have distributions of the different predicted probabilities for our data. On the right-hand side, we have the predicted probabilities for all the positive cases. On the left-hand side, we have the predicted probabilities for all the negative cases. So let's look a little bit more at how this is actually calculated. Remember, I told you that when we have a model that predicts probabilities, we typically use the threshold of 0.5, above which we classify as 1, below which we classify as 0. But we don't have to use that threshold. In fact, what an ROC curve does is it tries all of the different possible thresholds and tells you how changing that threshold affects the true positive and the false positive rate. So again, we're going to have our true positive rate on the y-axis and our false positive rate on the x-axis. All right, so let's try our first threshold. We're going to try a threshold that's right here. For this, we're going to classify anything to the right of the threshold as a positive case and anything to the left of the threshold as a negative case. Now, a true positive is when we have a positive that we actually classify as a positive. When we use this threshold, basically nothing is getting classified as a positive, so our true positive rate is practically 0. However, on the bright side, our false positive rate is also near 0. If we're not classifying anything as positive, then we have no false positives. So we're going to add a point to our graph right here at 0, 0, because when we use this threshold, our false positive rate and our true positive rate are essentially 0. But that's not the only threshold that we can try. Let's try this threshold. In this threshold, everything to the right is classified as a positive, everything to the left is classified as a negative. Now, on the bright side, using this threshold, about 50% of our actual positives are classified as being positive. So our true positive rate is more around 50%. And lucky for us, our false positive rate is still pretty low. While there's some data that's going to be classified as a positive when it's really a negative, that rate is really low. We'll say just a couple percent. So we're going to add another dot to our plot. We have about a 50% true positive and a couple percent of a false positive. Now let's try yet another threshold. Let's say about right here. Using this new threshold, our true positive rate has increased even more. Probably about 80% of the actual positives are being classified as positive. On the other hand, now that we're using this threshold, our false positive rate has gone up a little bit. I'd say maybe about 20%. So we're going to add a new dot to our ROC curve. Our true positive rate is about 80 and our false positive rate is about, let's say 20%. Now we try yet another threshold. Let's say we try one about here. Here, everything to the right is going to be classified as a positive, everything to the left is a negative. So at this point, our true positive rate is nearly 100%. Almost all of the actual positives are being classified as a positive. On the other hand, our false positive rate is climbing rapidly. Now a little more than 50% of our negatives are classified as a positive, giving us a very high false positive rate. So we're going to add yet another dot. Our true positive rate is around 100%, but our false positive rate is now around 50%. And last but not least, let's try this threshold. Using this threshold, everything is classified as a positive and almost nothing is classified as a negative. Now, on the bright side, our true positive rate is going to be 100%. Everything that is actually a positive is being classified as a positive. On the negative side, all of our negatives are being classified as being positive as well, so our false positive rate is also near 100%. So we're going to add that last dot right here on our curve. When we connect these points, we get the ROC curve. And once we have that curve, we can calculate the area under the curve to get our ROC AUC value. This one's going to be probably high, probably in the high 80s or the 90s, because most of the graph is below this curve. This means that our model is good at distinguishing between the positives and the negatives in our data set. You can see this visually in this plot because the predicted probabilities for the positive data points are often a lot higher than the predicted probabilities for the negative data point. All right, so we just talked about a bunch of different metrics from accuracy to ROC AUC that can help us assess the performance of the model. But one other thing I want to talk to you about is calibration. Calibration measures whether the predicted probabilities are accurate. If we predict a 40% chance of something being positive, does it really have a 40% chance of being positive? So let's look at this example. Here we have a model that is trying to predict whether or not a picture is of a dog. All 5 of these images here have a predicted probability of 80% of being a dog. Good calibration would mean that of these images, 80% of them actually are dogs, because on average, we predicted that they have an 80% chance of being a dog. And that actually is true here. If we look at our 5 images, 4 of them actually are dogs. This one's a false positive, which is a cat. This means that our model in this case has really good calibration. When it predicts that there's an 80% chance of something, there actually is about an 80% chance of it happening. Now let's look at another model that looks at these same images but has very different predicted probabilities. This model predicts for each of these images that they each have a 51% chance of being a dog. Now, one interesting thing to note here is that both of these models would make the exact same binary predictions. If all we're trying to do is predict whether or not something is a dog, both of these models would have an 80% accuracy because all of these would be classified as dogs because they're 80%, but so would all of these at 51%. However, the calibration of this second model is severely off. On average, these 5 pictures have a predicted probability of 50%, but 80% of them are actually dogs, which means our model is not well calibrated. We can't really trust the probabilities we're getting from the model. It still often makes the correct prediction, but the probabilities that we get out of the model just are worthless. The way that we assess calibration for a model is we take all of the different predicted probabilities for all the data points that we have, and we put them in order from smallest to biggest. Then we decide how many bins that we want. This is how many groups we're going to group all of those probabilities into. Typically, we'll do something like 6 or 10. Once we create these groups, what we're going to do is we're going to look to see whether the predicted probabilities are the same as the actual probabilities. First, let's calculate the average predicted probability. For this group of 2 here, the average predicted probability is 0.235. For this group, it's 0.41, etc., etc. Now we need to calculate the actual probability. We're going to do that by looking at the actual events that happened and calculating how many of them were positive. So here we've done that calculation. Now, because we only have 2 data points in a group, our probabilities can only be 0, 0.5, or 1. If we had more data, they could be a little more granular. For these 2 probabilities, the average actual probability is 0 because of these 2 events, 0% of them were a positive. And we can do the same exact calculation for all of these different groups. Now, visually, we can inspect this table and see that this doesn't have great calibration. There's pretty big differences between the average predicted probability and the average actual probability. Usually what we'll do is we'll visually inspect these calibration values by using something called a calibration curve. A calibration curve just basically plots these average predicted and average actual values on a plot. A perfectly calibrated model would have a calibration curve that looks like this, where the average actual values and the average predicted values are the same for each of our groups. By looking at how close our calculated calibration curve is to the ideal calibration curve, we can assess the calibration of this model. This is an example of calibration curves for both the training and the testing set for a model. We can see here that for the training set, our calibration curve is very near ideal, which is common for logistic regression. However, when we look at the testing set, our calibration curve gets a little worse. Now, one thing I want you to think about is whether or not calibration actually matters if our goal is just to make sure that we're making the correct prediction. Now I want to talk a little bit about how to interpret logistic regression models. So in our last logistic regression lecture, we talked about 3 units that we might possibly use so that we could use a linear regression to predict an event as either happening or not happening. The first one we tried were probabilities. Probabilities range from 0 to 1, and one benefit of probabilities is that they're pretty intuitive. Almost everyone in your life understands what a probability is. Next, we talked about odds. Odds range from 0 to positive infinity, and while they're less common than probabilities, most people still kind of understand what they are, especially if you're really into gambling. Last but not least, we talked about log odds. Log odds range from negative infinity to positive infinity, which is one reason why they work so well when using linear regression to predict a categorical event. However, one downside of log odds is that they're almost completely uninterpretable. If you went up to anyone, including me, and asked them what a log odd really was, I'm not sure they would have a great answer for you because log odds are a little bit difficult to understand. Now, with these 3 different units, we have different thresholds that we want to think about. Remember, probabilities range from 0 to 1, and the threshold that's important to remember is 50%. 50% is the threshold above which an event is more likely to happen than not, and below which it's less likely to happen than not. Odds range from 0 to infinity, and the important threshold here is 1. Odds above 1 indicate an event that is more likely to happen than not. Odds below 1 indicate an event that is less likely to happen than not. And last but not least, we have log odds. Log odds range from negative infinity to positive infinity, and the important threshold to remember here is 0. If we see something with positive log odds, it's more likely that that event will happen than not. If we see something with negative log odds, it's less likely to happen than not. All right, so using all of those ideas that we just talked about, let's talk a little bit about how we can interpret the coefficients of a logistic regression model. Now, because we're using linear regression to predict log odds, the natural values of the coefficients that you're going to get from your model are going to be in terms of log odds. Here's a graph that looks at the impact of the intercept on a logistic regression model. Here you can see a bunch of different sigmoid or logistic curves with different intercepts. As our intercept increases, it moves our curve towards the left. Basically, what this means is that it takes smaller values of our predictor in order to get a predicted probability above 50%. Now, let's look at the impact of our coefficient. Here you can see different logistic curves with the same intercept but different slopes. First of all, let's look at these three curves here. Here we have the three curves that all have positive slopes, and these look like our typical S-shaped curve. As our predictor increases, the predicted probability increases. If we see a negative, then we're looking at these three curves. These have an inverse relationship. As we increase our predictor, the predicted probability actually decreases. And you can see the bigger in magnitude a coefficient is, so the further it is from zero, the steeper the curve is. That means that smaller changes in our predictor produce larger changes in our predicted probability. So what does this all mean? Well, as I mentioned before, when you get the coefficients from your model from logistic regression, they're going to be in terms of log odds. So we often call these the log odds coefficient. And these can actually be interpreted pretty much the exact same way that a linear regression coefficient can be. And that makes sense because a logistic regression is basically a linear regression predicting the log odds. So for instance, for age, we would say that an increase in 1 unit, so maybe a standard deviation, maybe a year, an increase in 1 unit in age causes our predicted log odds to increase by 0.14. Similarly, we could do that for income. We can say as income increases by 1 unit, whether or not that's a standard deviation, our predicted log odds decrease by 0.006. However, as we talked about before, log odds are basically uninterpretable. Like, what does a log odd even mean? I'm not sure. So typically with our log odds coefficients, what we're looking for is just whether the relationship is positive or negative. So for instance, from this model, we can tell that age and months subbed have a positive relationship with our outcome, whereas income has a negative relationship. Now, one thing that's really nice about log odds coefficients is that they're symmetric. And what I mean by that is if we have a coefficient that was -2 and then a different coefficient that had a value of 2, those two effects are the same size, just in opposite directions. And this turns out not to be true for the other types of coefficients we're going to look at. All right, but like I mentioned, log odds are pretty much uninterpretable. So while it can tell us just by a glance the direction of our effects, often we want to present our results in a bit more of an intuitive way. So usually what we do is we present the odds coefficient. Now remember, if we take the log odds and we exponentiate them, so we take e to the power of the log odds, we get back the regular old odds, because remember, a log undoes an exponent. These odds coefficients are now in terms of something that's a little more intuitive to people, the odds. However, there is a bit of a difference in their interpretation. When we're talking about odds coefficients and how they change our predicted odds, we actually are talking about multiplication, not addition, and I'll tell you what I mean. So let's look at this effect of age. The odds coefficient is about 1.15. What this means is that as age increases by 1 unit, whether or not that's a standard deviation, the predicted odds are multiplied by 1.15. In other words, they increase by 15%. For income, we can see that as income increases by 1 unit, whether that's a standard deviation or not, the predicted odds are multiplied by 0.99. In other words, they reduce by, about 1%. Remember that we talked about that with odds, the important threshold to remember is 1, and that's true for the coefficients as well. Any coefficient with a value above 1 is going to increase or have a positive relationship with our outcome, and anything with a coefficient below 1 is going to have a negative relationship. As that predictor increases, the predicted odds are going to decrease, because if we multiply a value by something smaller than 1, it's going to get smaller and smaller and smaller. So we covered log odds coefficient, and then we covered odds coefficients, which are a little bit more interpretable to people because they understand what odds are. So why don't we try some probability coefficients? Well, the answer is we can't, and I'm going to tell you why. Looking at this graph, we can see two really important things. The first one, if we look at the log odds graph, is that the relationship between our predictor x and our log odds is constant. Anytime we increase our predictor value by 1, the predicted log odds increase by the same amount. So there is a constant value that represents the relationship between our predictor and our predicted log odds. It's the coefficient. Now, looking at the odds graph, we can see that we don't see that straight line, but there is a consistent relationship. Every time we increase our predictor by 1 unit, our odds are multiplied by the same value. That value is the odds coefficient. Both log odds and odds have a constant relationship with our predictors. There's a single number that can represent those relationships. For log odds, it's the value that we add each time we increase our predictor. For odds, it's the value that we multiply by each time we increase our predictor. However, when we look at probabilities, what we see is that our predicted probabilities do not have a constant relationship with our predictor. This is because as we increase our predictor by 1 unit, the amount that the predicted probability changes is different depending on where you are in the curve. For example, at the extremes of a curve, increasing the predictor by 1 unit has barely any impact on the predicted probability. But if you're in the middle of the curve, it has a huge impact. As you increase by 1 unit, the predicted probability increases by a lot. So because the relationship between our predictor and our predicted probability is not constant, it means there's no single number that can represent the relationship between our predictor and the predicted probability. And for that reason, it's not possible for us to use probability coefficients because there's not a single number that can represent that relationship like there is with odds and log odds. So while probabilities are the most intuitive units of all three, we typically don't present our results from a logistic regression in terms of probabilities because there is no one number that we can use to represent the relationship between our predictors and our predicted probabilities. For log odds and odds, there is a consistent relationship, although log odds are a bit uninterpretable, so often we want to present things in terms of odds. Last but not least, you might notice this caution sign here. I just want to say we're not going to go over it here. There are some ways that you can use probability to present the results of your logistic regression, but coefficients is not the place that you can do that. All right, that's all I have for you. I will see you next time.